So you might remember from the video on atomic structure that we said the electrons in an atom occupy these things called shells. These can also be called energy levels. So we're going to talk a bit more about shells and how the electron arrangement within the shells links to how elements are arranged in the table. So if we look at the shells, the electron shell with the lowest energy is filled first. And this is the one closest to the nucleus. So we fill the ones which are close to the nucleus before filling the ones which are further away. And there is a certain number of electrons, certain maximum of electrons which can occupy each shell. So for the first shell, the one closest to the nucleus, we can have 2 electrons occupying it. For the second and third shells, we can have a maximum of 8 electrons. So what I'm going to do is run through 3 examples of electronic configuration diagrams using 3 different elements. Helium is our first example, and we can find the number of electrons in a helium atom by looking at the atomic number, and you might not be able to see that, but it is 2. Now we can fit 2 electrons into the first shell, so in the case of helium, only the first shell is needed to fill all the electrons, and we're going to represent the electrons using crosses. If we look at boron as our next example, boron has an atomic number of 5, and of course that means in an atom it has 5 protons, but it also has 5 electrons. So what we do is we fill the first shell by adding 2 electrons, because that's all we can fill, that's the maximum, and in the second shell we fill 3 electrons. So we put 2 electrons in the first shell, 3 into the second shell, and that's 5 in total. Now with magnesium, magnesium has 12 electrons. So what we do is we fill the first shell completely, and we fill the second shell completely. So we put 8 electrons into this second shell. And we do that because at this point we've only filled 10 electrons, and obviously magnesium has an atomic number of 12. So we need to put 2 more electrons into this third shell. And this is the configuration for magnesium. So the first one we did, which was helium, helium had a full outer shell of electrons. And it's worth mentioning, just as a side note, that atoms with full outer shells are more stable in the sense that they don't react as easily compared to other atoms with incomplete outer shells like boron and magnesium. So these diagrams are one way to show an atom's electron configuration, but we can also express it using numbers. So for helium, there are only 2 electrons and of course 1 electron shell. So we write 2. For boron, we have 5 electrons in total, 2 occupying the first shell and 3 occupying the second shell. And magnesium, we have 2 occupying the first shell, 8 occupying the second shell, and 2 occupying the third shell. And these are the configurations written out like this. Now the specification says you only need to know this for the first 20 elements in the table. So basically any element which contains 20 or fewer electrons. So something to be spoken about which is really important is the link between where an element lies on the table and its electronic configuration. So a rule that we can use when dealing with the first 20 elements on the periodic table is that the group number defines how many electrons are on the outer shell. So for the elements in group 1, they have 1 electron on their outer shell. For the elements in group 2, they have 2 electrons on their outer shell, and so on. The only exception to this rule is the group 0 elements, which are here right at the end on the right. All the elements in the group 0 column have full outer shells. Neon and argon have 8 electrons on their outer shell, and helium has 2. So instead of calling this column group 8, which might make sense considering we have groups 3, 4, 5, 6, and 7, it wouldn't actually be true if we call it group 8 in respect to this rule. So what we do is we refer to it as group 0. But the table can tell us more than just the number of outer electrons for an element. The periods tell us how many electron shells a particular element has. So if we look at, for example, phosphorus. Phosphorus is in the third period and it's in group 5. Because it's in period 3, we know that phosphorus has 3 electron shells. If an element has 3 electron shells, that means the first 2 electron shells are full. And so we have 2 electrons in the first shell, 8 in the second one. And to find out the number of electrons in the third and final outer shell, all we need to do is look at the group number, which is 5. And so this is the electronic configuration for phosphorus. And I didn't even have to look at how many electrons phosphorus has, which is 15. All I had to do was look at the period number and the group number, and I was able to write out its configuration. So this page kind of summarizes how you can work out the electronic configuration of an element just by looking at its position in the table, as we've just done with phosphorus. The number of electron shells of an element is given by the period number. And the group number tells you how many electrons occupy the outer shell. So you know if an element is in period 3, it has 2 full shells of electrons, and the number of electrons in its third shell is given by the group number. Obviously with the exception of group 0, as we've mentioned. So to finish off this video, I've put together a table to show the electronic configuration of the first 20 elements as per the specification. You don't need to know anything after 20, and especially not halfway through this 4th period, because it does get slightly more complex after that in terms of electron arrangement within shells. Just remember that 2 electrons can occupy the first electron shell, while 8 can occupy the second and third shells. So you can pause the video and I'll show the completed table on the screen in a few seconds.